Welcome to The Explainer. Today, we're embarking on a really fascinating but entirely invisible translation journey. Think about it. Every single day, you're interacting with digital devices, typing messages, writing emails, searching the web. But have you ever stopped to wonder about the massive, silent translation engine running constantly underneath the glass and plastic of your screens and keyboards? That engine is literally converting your human intent into the cold, raw physics of a machine, millions of times a second. Today, we're going to decode that engine together and explore the Rosetta Stone of computing.
Okay, let's dive into this because honestly, it is just so easy to take for granted. You press a key and a letter instantly pops up on your screen. But a computer chip, a raw piece of silicon, it doesn't know what an A is. It doesn't understand language or art or the alphabet. It only understands voltage. It's either on or off, high or low. So how exactly do we bridge that massive gap between a human concept, like the very first letter of our alphabet, and microscopic electrical currents? To really get this, let's trace the life of just one single keystroke across three distinct zones. It all starts in what we'll call the physical zone. You physically press the A key on your keyboard. That action instantly jumps into the logical zone, where a mapping engine translates that human letter A into a decimal number, in this case 65. But the machine still can't read 65, right? So it passes into the machine zone, where a conversion engine transforms it into binary, 100001.
Section 1. The Computing Rosetta Stone. So now that we've mapped out the overall zones, let's look at that very first critical step. Because computers rely entirely on a binary language of zeros and ones, every single human symbol must first be translated into a mathematical cipher. We call this process encoding. Think of it as a massive, globally agreed-upon lookup table. If I want to type an A, the computer and I both need to agree on exactly what numerical value represents A. Without encoding, human-computer interaction simply wouldn't exist.
Now, what's really interesting about this is how our digital dictionary had to evolve as computing went global. Back in the 1960s, we had ASCII. It was a 7-bit structure with room for just 128 characters, which was basically enough to fit a standard English keyboard and some control codes, and that was about it. But that obviously wasn't nearly enough for the whole world. By the mid-1980s, we saw expansions like ISCI, which added an 8th bit to include Indian scripts. And today we have Unicode. Unicode is the universal standard. It incorporates literally every written language in the world. Take the Hindi character, for example, representing the hex code 0905, flawlessly translating into its corresponding binary string. Unicode ensures absolutely no human language is left behind.
Section 2. The Number System Taxonomy.
Okay, so we've got our dictionary, but how does the machine actually process those numbers? Well, this taxonomy lays it all out for us. The core concept to grasp here is the base or radix. That's simply the number of unique literal symbols a system uses to build all of its math. We humans, we live in base 10, using digits 0 through 9. Computers, they live in base 2, using only 0 and 1 to represent physical transistors. But as we're going to see, programmers also use base 8, which is octal, and base 16, hexadecimal, as highly efficient shorthand systems to make sense of the whole shebang.
Section 3. Binary. The machine's grammar.
All right, let's step away from our human comfort zone and go deep into the machine zone. I know it's easy to look at binary and just feel instantly intimidated, but let's contrast our super comfortable day-to-day counting system with the machine's strict on and off limits. In our decimal system, we count in powers of 10, right? Units, tens, hundreds. In binary, the machine simply counts in powers of 2, units, twos, fours, eights, and so on. What's absolutely crucial to realize is that both are fundamentally positional systems. The rules are exactly the same, literally only the multiplier has changed. Think about our familiar decimal system for a second. The number 237, that just means 2 hundreds plus 3 tens plus 7 units. A symbol's value depends entirely on its position relative to the base multiplier. Now apply that to the alien binary system. The string 101 works exactly the same way. It's just 14 plus 0 twos plus 1 unit. Add those up, 4 plus 0 plus 1 equals 5. It is just beautifully logical. So you might be wondering, if we have a decimal number, like our letter A cipher 65, how do we mechanically turn that into binary? It's actually an incredibly simple 3-step procedure that you could do on a napkin right now. First, divide your number by your target base, which is 2. Second, write down the remainder. Third, keep dividing the result until you hit 0.
And then just read your remainders from bottom to top. That's it.
And this brilliantly illustrates exactly how it works. Let's watch this process cascade down the waterfall. We start with our decimal 65 entering the top. Divide 65 by 2, and you get 32 with a remainder of 1. We write that 1 down. Then we take 32, divide it by 2, which gives us 16, remainder 0. We write the 0 down. We just keep flowing down the waterfall until we reach 0. Finally, read those remainders back up from bottom to top, and there it is, 1000001. We have just successfully translated a human concept into machine physics.
Section 4. Hexadecimal. Visual compression.
But here's a very practical problem. While a machine absolutely loves reading a string like 100,001, for us humans, endless screens of ones and zeros are a total nightmare to read, debug, or memorize. We desperately need visual compression. And this brings us to an incredibly elegant solution, the intuitive visual metaphor of the scissors technique. Because 8 and 16 are powers of 2, they map perfectly onto binary. If we want to use base 8, octal, we just take our imaginary scissors and cut the endless binary string into neat 3-bit slices. Those 3 bits will perfectly encode one single octal digit. Even more brilliantly, if we want to use base 16, hexadecimal, we just cut the binary into 4-bit slices. It acts as an instant, high-efficiency visual compression interface for humans.
Now, working in base 16 means we actually need 16 unique digits. And since we humans only have 0 through 9, we have to borrow the alphabet. So A is 10, B is 11, all the way to F, which is 15. So if we look at a hex string like 3A5 and want to convert it back to our native decimal, it's just math again. Think about it. 5 times 16 to the power of 0. A, which remember, is 10, times 16 to the power of 1, and 3 times 16 squared. Multiply them by their positional base value, add them up, and 3A5 instantly resolves to the decimal 933.
Section 5. Synthesis and real-world application. Let's move to and see how this builds into the actual digital environments you interact with every single day. Inside your computer, the main memory relies on massive 16-bit or 32-bit hardware addresses to locate data. Imagine trying to read thousands of those raw 16-bit binary strings. It's impossible. Instead, hexadecimal acts as a vital shorthand. By applying that slicing technique we talked about, that massive unreadable binary string collapses into a neat, memorable, 4-character programmer shorthand like C0F1. This is exactly how software engineers actually navigate the physical memory of a machine.
But it gets even cooler and a lot more visual. Hexadecimal isn't just for memory addresses. It is literally painting the internet. A standard digital display uses a palette of 16 million colors, which requires 24 bits of data per pixel. That's 8 bits for the red channel, 8 for green, and 8 for blue. Programmers translate those 8-bit binary strings directly into hex codes. Think about just the red channel for a second. If you turn it all the way up to binary 11111111, that translates perfectly to the hex code FF. Mix it with zeros for green and blue, and you get the exact color value FF000. That's a pure red. It's how every single color on every web page you visit is defined.
So, the crucial point is, when we bring this all together, we realize the digital world is just an endless, silent translation. Your human intent, pressing the letter A, passes through an encoding standard dictionary like Unicode to become a globally agreed-upon decimal cipher, 65. It drops down that division waterfall we saw to become the raw machine state of 1000001. And ultimately, for human programmers to actually manage it efficiently, it gets sliced and compressed into a system shorthand, the hexadecimal 41.
We basically mapped the entire journey, from a physical press of a key all the way down to the microscopic switching of electrical states. Encoding schemes provide the dictionary, and these number systems provide the underlying grammar. So the next time you send a text or type in a web address, I want you to take a look at your keyboard. Can you picture that endless silent cascade of math happening right beneath your fingertips? Thank you so much for exploring the Rosetta Stone of computing with me on this explainer. Keep learning and keep decoding the world around you.